Good evening, everyone. Welcome to the Astro Imaging channel. For those of you who don't know me, which is probably pretty much everyone, I'm Patrick Spencer, and I'll be the host for tonight's show. We've got a good show for you tonight. We've got Ivo Stoynov is here with us, and Ivo is the creator of the imaging software Astro Photography Tool, or APT, which I imagine some of you have used. And so tonight he's going to talk to us about focusing. But before we get to the presentation, let's just take a quick look at the calendar. Let me share my screen here. All right, so we've got some pretty interesting programs coming up here over the next few weeks. Next week, we've got Alyssa Pagan, and she's from the Space Telescope Science Institute, and she's going to be talking about the James Webb Space Telescope imaging and how they take the infrared data and make color images out of it. And then the next week we've got John Hayes, and he'll be here to tell us about some of his adventures with remote imaging down in Chile. And then we've got Sid Fried coming back, and some of you may remember he was on before, and we had a bit of a glitch during his presentation about his astrophotography journey. So we're having him come back to finish that story. And we've got a number of other shows. I think we might have someone lined up for August 13th. If not, that's an opening. And then we do have we've got a full calendar until the mid-September, at which point we do have openings. So you all know the drill, but if anyone has a topic, something that you'd like to share, talk about on the Astro Imaging channel, just contact us through the website, send us an email, we'll get in touch with you and get you set up onto the schedule. So let me stop sharing here. All right, so the last few weeks, we've touched on some really foundational elements of astrophotography. A couple of weeks ago, we had Adam Block on, and he talked to us about stretching astro images. Last week, we had Frank Sackenheim, and he talked to us about removing gradients with Graxpert. So tonight, we're really continuing with that theme. As I mentioned, Ivo tonight will be talking about focusing, and really it doesn't get any more fundamental than focusing. If your focus is off, then you just can't get good data, regardless of whether or not everything else may be working flawlessly. And I'm sure we've all had nights where everything seemed to be going well. We thought we were getting good data, and then, oops, we realized that we had a problem with our focus. And then the data had to be tossed. So at least I know I've had that situation happen to me. So anyway, Ivo's here to help us try to avoid those issues. So Ivo, are you ready to take over the screen?
Yeah.
All right. Well, whenever you're ready, you can share and start presenting.
So the idea of this presentation is to show all the elements, all the aspects of the focusing as kind of summary, not going in deep details in every aspects, but just mentioning what are the important points. So no matter if you're a beginner or advanced imager, so you can find something interesting and useful. I hope so. The presentation will be focused on achieving good focus for deep sky imaging, not for planetary imaging. And I have separated the information in 4 parts. visual focusing, computing powered focusing, automatic focusing, and refocusing. Uh, the name of the presentation is Focus A to Z. So this is what can be defined as the place where everyone starts using optical instrument is somewhere in this Bermuda Triangle of the spyglass, pirate spyglass, the first binocular you have used, or the this magical device, the knob of the uh, first telescope you have watched for first time through. No matter how you start and what instrument you are using, the goal is to get clear image, and this gives possibility to use the full potential of the telescope, the instrument. When we are we start to image, usually we try starts to focus by the same way as we are using the telescope visually, trying to find the best position which the stars are smaller. So when we are using DSLRs, it is good to select high ISO and also to use the live view feature of your camera in order to save the shutter life. When you are using CCD camera, CCD or CMOS camera, it is good to use mid-range or high range value of the gain in order to get more clear image of the star. In this case, my personal opinion is that using images to focus are better than live video, because the images are giving possibility to make a little bit longer exposure, and when we are using longer exposure, the influence of the atmosphere is smaller, and we can see better how good are the focus changes we are doing. Several hints I want to mention when we are focusing. The first one is to select the brightest stars from the same side of the meridian as the target viewer image. Some telescopes like Smith-Cassegrain, especially the older models, doesn't have possibility to walk the mirror, and if you change the position of the scope according to meridian, it is possible to experience mirror flow, and this will change the focus. So keep from the same side of the meridian when you are focusing. Also, it is very good to use a star as close as possible to zenith. When you are pointing the telescope up, the amount of atmosphere between the star and the telescope is smallest, and the influence of that atmosphere is smallest. So try to use the stars high in the sky for focusing, but beware about the possibility to hit the tripod or the, and watch not to hit the tripod and damage your kit. When we are focusing, we always come to a moment when we make changes but doesn't see any improvements in the image quality, and this is caused by something named critical focus zone. On the image, you can see a very popular presentation how a telescope is focusing two beams in the focal plane. The two beams are intersecting in one point in the focal plane. However, the angle between these two beams is kind of sharp, and at one point they are so close that we cannot distinguish if they are already intersected or not. Especially when we are using image sensor, the resolution power is limited, so there is a range of positions where the image is equally focused for us, no matter that it is not exactly the focal plane. So this area is named critical focus zone, and it depends on the speed of the telescope. Here you can see the formula, which is giving how many microns are the critical focus zone, and it is mostly influenced by the focal ratio. If we are using slow telescope, the critical focus zone will be wider, and this means that we have more positions where the image is good, while when the telescope is fast, in this case, the critical focus zone is very narrow, so it is very important to get very good focus when we are using fast telescopes. So if there is a hint that we are in the critical focus zone, it will be very useful thing. In this, in order to get in order to get sign that we are in the critical focus zone, we can use two features of the light. This is diffraction and the interference of light. The diffraction is light bending of the light when it passes through the edge, around the edge of an object. The interference in interaction of two waves, and if these two waves are with same phase, it leads to increasing the wave amplitude. So when you are using a telescope with a secondary mirror that is held by a spider, we have possibility to observe these two features of the light, because the spider is diffracting the light, and because it is same light, it is same wave. The wave is with the same phase, and this is causing interference. So when we have a star and spider, we can see spikes caused by the amplified diffraction, which is something we have used to see. So when we are focusing and there is no other tool we can use, it is possible to watch for the spikes caused by bright star. And when the spikes are most visible, we are very close to the good focus point. Most likely, we are in the critical focus zone. During all the years after invention of the telescope, finding the good focusing position was never-ending quest, and many people are trying to find ways to make the focusing easier and more predictive. Around the year 1900, the astronomer Johannes Hartmann invented a special tool named Hartmann mask. It is a disc put in front of the objective with two holes, and these two holes are causing diffraction of the lights, and as a result, we will see two bright images when the telescope is not focused. When we are reaching the focus plane, we will see that the two images are getting closer and closer, and when the telescope is focused, these two images will join in one. Again, when you pass through the away from the focus in inner direction, the two images will start to separate wider and wider. Using the diffraction of the light and making different shape and count of the holes is possible to get a different number of images and different shapes. In the image in right, you can see example for different Hartmann masks. The first one is using triangles, which is introducing kind of interference in the end image, and when uh, the three spots are collided, the resulting image will show in addition spikes in order to get better presentation about the fact that we are in the focus point. So during the years, many experiments were made with Hartmann masks, and one of them is that if we replace the round dots, the round circles with rectangles, orthogonal rectangles, in the focus point, we'll get a nice bright plus sign. So adding more rectangles with different shape and different angles is producing different images, and the idea is that multiplying the rectangles are multiplying the interference, producing better spikes. As an end result of this process can be considered the invention of the Bakhtinov masks, which is with shape and structure well known now. In the middle, you can see that the blue and the green part of the mask are producing the outer spikes, which are defining an angle. And a red part of the mask are producing another spike in the middle of in this angle. When we reach the exact focus point, the middle spike will be bisecting exactly the middle of the angle, and this is the sign that we are in a position with very good focus point, focus in a position with very good focus. When we have a connection between the camera and computer, we can use the computer to make calculations for us and to simplify the process of focusing. Many applications are possible to analyze the image from Bakhtinov masks, including KPT. And during analyzing of the image, sometimes it's happening that the software is not possible to detect the spikes correctly. In such case, a handful trick is to rotate the mask, usually by diagonal of the sensor. In this direction, when the middle spike is near the diagonal of the sensor, is a position when is best detected by software. Also, when we are focusing with narrow band filters, the spikes are not lines but a series of dots, which sometimes is difficult for the software to detect. An empirically found trick is that if we use a luminous filter or broadband filter, just to detect the spikes, and after that change the filter and continue the focusing. Usually the software is using the initial detection, and it's making easier to focus narrowband filters with a mask. When we have a connection to the computer, in addition to the Bakhtinov mask, we can measure the stars, the size of the stars by different ways, and by that, but that way to, but that these ways to see how good are the focusing changes we are making. There are three methods. Two of them are very well known. The third is something new that I hope that you will find interesting. All the three are for measuring the star size. The first one is the oldest one, is the full width half maximum. Sorry, just a second. It happens that the stars, the image of the stars has a special feature of its brightness. It is distributed by such a way that it can be described by a function with a specific feature named Gaussian function. So the idea of full width half maximum is to locate the point with the highest brightness in the star image, and to take one line that includes from the image of the star, which includes that highest brightest point, which is named star profile. And after that, to analyze the brightness levels of the star profile, make a curve fit, which is calculate what is the parameters of the Gaussian function, which correspond to the brightness of this profile. When we calculate, we make this curve fit, passing the brightest value to the function is possible to allow us to calculate what are the positions of the points with half of the maximum brightness. And these are 2 points, and the distance between them is something we can use to measure how wide the star is. When we are getting closer to the focusing position, the peak is getting narrower and taller, and the distance between the 2 points in the middle of the brightness are getting closer, each one closer each one together, and the number of full width half maximums is getting slower. So the best focus position is the place when where that size is smallest. The disadvantage of this method for measuring stars is that it is slow to compute the curve fitting of the Gaussian function, and because we are using just one line from the star image, it is very affected by the turbulence of the atmosphere. It is possible to make a 3D model of the star, but it is even slower, and there is a better way to do that. This is a newer method named half-fox diameter, which works not with one line, but with area of the star image. In short, the method is to detect what is the level of the background, the sky background, and to detect what is the highest level of the brightness of the star image, and to work with area which is roughly the half of the brightness of the maximum. Uh, and when we are working with this circle, we are computing a lot of pixels, and this gives us much better accuracy, and it is less affected by the turbulence. Additional advantage is that we don't make any curve fitting. It is just evaluating signals and distances, and the computing is very fast. The disadvantage of this method is that when the star is very defocused to the level of donut, it is possible that the calculations start to measure part of the star, not the whole image, but just part of it. So it is something that should be considered. The third matrix I want to cover is something that is invented and implemented in the APT community. It is suggested by Chen Yan Tan, and together with Benjamin Schultz, they came with final solution and computation about the mathematics, the mathematical part of the this idea. The idea is based on a mathematical transformation named Fourier transformation. I don't want to go in deep details, but Fourier transformation is giving presentation what is the frequency of a function, and as a result, it gives way the star to stand more above the surrounding background. So Chen Yantan found that if he apply Fourier transform on a star image, and after that integrate the values given from the transformation, the result will be one big number, which he named star power. On the image from left, you can see how is what is the original image, and in the middle is how it looks when Fourier transform is applied. When the star is better and better focused, the corners, the pink corners areas, are getting bigger and more prominent, and this is a sign that we are getting to closer to the focus. In the right image, there is comparison what is the result of the Fourier transform from about good and bad focused image. So the star power is very big number, and it is getting bigger when you're getting close to the focus, which is something we are not used to when we talk about focusing metrics. We expect that the number should get smaller when we are close to the focus. So decided that we will inverse that function, and we'll divide 1 by the power. So this is the reason to name the end result inversed power. Also, because the numbers are very big and hard to read and understand, there was need to make a new presentation of the numbers. So when we have 3.63 multiplied by 10 on power 14, it is easier to compare numbers when they are represented with the number of the power and following the other part of the number. So when we have 16 pipe 332, it is bigger than 15 pipe 763, and this is bigger than 15 pipe 546. So when we are focusing, we should look for first getting the first part small, and when we fix that part, to look how the second part of the number is changing. Here in the screenshot, you can see how is looking at tool in APT, which is using the inverse power. You can see the graph, how it is getting down when we are closing the focus position, and uh, how it is getting back up when we passed through that point. There is advantages from this for this method. It is very fast to compute. It works with short exposures. Short, I mean, when we need 6 or 7 seconds for half Hertz diameter, for inverse power, we can use a second or half a second exposure. Also, uh, while the half Hertz diameter needs to detect the stars in the images and to evaluate each star uh, individually, the inverse power is working with the whole image at once without needing to know where the stars are. The only disadvantage of this is that inverse power is very affected when there is saturated stars. So when we are using different filters, we have to find good exposure that is not giving saturated images for broadband filters, and to use other exposure, usually a little bit longer, uh, for the narrowband filters. Um, so when we are focusing manually, there are several ways we have already covered till the moment, and this is a list how good is way to achieve focus from least to most accurate by eye when we are making changes only evaluating the star by eye. It is the least accurate method. Using the spider gives additional feedback, which is uh, allows us to get a more accurate idea how the focus is. Focusing mask is a much better way to get to good focus. I can compare it with full half maximum or something. Maybe they are on same level, and the most accurate ways are the half Fox diameter and inverse power. Uh, for the last two options, of course, we are looking for the place where we are getting the smallest numbers. Once we have get a good focus, we should keep it. We know that the focus is changing during the night, so, we should take care to keep the telescope focused during the night. When the temperature changes, the parameters of the telescope are changing, and in almost every case, you need to take care and to refocus. Just some quite a few models of telescope are very stable to temperature changes. Uh, when we are using filters, you have to focus when you change filter. No matter how the producer are explaining that they are parafocal, there are always small changes between the focus with different filters. Even mounting the way you have mounted the filter in the filter wheel is possible to introduce difference in the focus. So when you change filter, always make a new focus. When you change DSLR battery, usually you are changing the focus. So make sure to refocus after that. And another case is when you are rotating the camera. Usually, not usually you are losing a bit the holder of the camera rotating, and this is changing the position. Unless you have a rock solid focuser, if you touch the camera, consider that you should refocus. So in this case, the computer connection is in very big help. It saves you the need to manipulate the camera manually. You can make it remotely. And in this we are in the middle of the presentation, so if there are questions related to the manual or visual focusing, maybe it is a good moment to address them.
Hi, Ivo. Yeah, there are a couple of questions, some of which you might be covering a little bit later. Do you have a recommendations on how to get the best focus on an OAG? And is that somehow different than
The best focus on?
On an OAG off-axis guider?
In fact, it is almost the same like focusing the main telescope. In order to get it, first make a little computation measuring what is the distance between the camera and the main camera and the prism of the off-axis guider. And after that, measure the distance between the prism and the guiding camera. These distances should be equal or near equal. And when you make that, you will have good starting point when the stars will be near focus in the off axis. When you focus the main camera, the guiding camera will be also near the good focus point, so you will start see images. Also, using the highest gain that the guide camera can handle and long exposure will show you the donut of the image in the guide camera, so you can start trying to get a better position.
Another question, what is the recommended exposure time based on unity gain for a good autofocusing with a typical, well, they said ZWO camera, but I suppose that applies to any of the CMOS cameras. How do you know if a star is saturated?
When you are focusing with half flux diameter or full width half maximum, the saturation is not very important because it is measuring the other parts of the star. But for inverse power, it is the sign that you are getting very saturated image is that when you are going closer to the focus position, the inverse power is getting higher. You will see that there is inverted curve of focusing when there is saturated star, and you should try to lower the exposure or lower the gain.
And the other question, can you discuss the effect of sensor back focus on getting the best star focus?
Sorry?
The effect of back focus.
Again,
Back focus, the distance that the sensor sits. So in other words, having back focus.
yeah, yeah.
In other words, your image comes to focus. I assume back focus is kind of another discussion.
The back focus is the space which you can use to find the focusing position. It is the amount of positions that the focuser can handle. So it is not related to the way you are measuring the focus. It is feature of the telescope and the focuser.
And I have another question. Is anyone implementing your third option on focus on some of their software programs?
I know that the other applications has started to implement similar idea about inverse power, but I'm not sure if there is other which is using exactly the same. By the way, the Benjamin Schultz wrote open source library, which is calculating inverse power on a given image. So it is possible to be implemented in other applications. The source code is coming with the APT installation. In the APT user guide, there is a link to the GitHub repository with that library, which is open source and can be used.
Those are the questions so far.
Thank you. Thank you. So, just a second. We can continue with the next level of focusing. When we add motorized focuser in the equation of focusing, it is giving us a lot of possibilities. And definitely it is something that everyone that is going seriously is in how to astrophotography is something that should be considered and added as soon as possible, because it is giving a lot of power. When we have way to move the focuser through computer control, it is possible to use different ways to make automatic focuser. There are three known methods about that which are currently used. The first one is two passes search, which is in fact kind of reproducing the way we are focusing manually. Before we discuss the method, let's get back to critical focus zone, because it is important about the accuracy of the focusing. So we already know what is critical focus zone and know that it is a number of microns. But in order to use that knowledge, we should convert somehow the critical focus zone in number of steps of the focuser, the motor focus, the steps of the focuser motor. It is not exactly mandatory, but will be in help. If your telescope is equipped with Crayford or rack and pinion focuser, you can use micrometer, digital or analog, to make two measurements, like on the given image. The idea is to move the focuser in out direction till you see movement, measure this distance here. After that, make another movement in out direction, let's say with 500 steps, and to make another measurement. So using this simple formula, we'll give how many steps represent 1 micron of change of the focuser position. So when we know that, we can compute how many steps the critical focus zone is wide. It can sound complicated, but APT has all the calculations included in it. I suppose that the other software has some tools to cover that also. So this is just idea why and how it can be made. So the first way to make automatic focusing is, as I said, copying the way we are focusing manually. It makes one pass analyzing the how the star image is changing, and by this way are finding where is the good the range, where is the good focus point. After that, with on a second pass with small fine steps, it tried to find the lowest value of the half Fox diameter, fluid half maximum, or inverse power. It is very easy to implement autofocusing, and every software that has autofocusing at one point has implemented it, including APT. The disadvantage of this model is that it is very important to pick up good, big, and fine steps, and this could be time consuming. Also, the selection of the fine step is very critical. If it is too big, if it's bigger than the critical focus zone, it is possible to make some changes and skip the range of the critical focus zone where the good focus point is. If the fine step is too small, then we are get a lot of jumping, a lot of samples with small difference in it caused by the turbulence, and we will not know if we are getting better or worse making these changes. So the end result may be not accurate, just because there is a kind of peak of turbulence, and after that calm time, and the method could decide that it reached the good focusing point when it is not. So in order to solve the problem about finding the position, in year 2001, Steve Bradley and Larry Weber, who came with the famous V-curve algorithm for finding good focus point, and they implemented one application named Focus Max. Also, they made a plugin for different applications which can use. The idea is behind that method is that we are gathering multiple samples. The samples are taking image, analyzing the quality of the focus, and we are doing that on different positions of the focuser. When we are collect good number of samples, we find one which is with lowest half flux diameter, and separate the samples in two sets. Every set is used to calculate one line that is closer to all of these samples. They will not lie on this line, but will be close to the line. And when we have two lines, there their intersection is in a point which is somewhere in the critical focus zone. It is very good algorithm. It was a gold standard for 20 years, and it is proof that it is very good way to find the focus. The disadvantage of this method is that it is separating the samples into sets. So when we are separating them in by that way, we are losing kind of accuracy, and the two lines could be more influenced by turbulence. Because of that, a new method was invented. Again, it came from the APT community. Everything started with the idea given by Stephen King that if we have a lot of number of samples around the focus point, these samples could be described with a hyperbola. And when we find that the formula of that hyperbola, we can calculate the lowest point, and that point is somewhere in the critical focus zone. So a lot of tests were made before starting implementing that, and many hours and tests and proof of concepts were made in order to build a tool which is giving a way to find the focus point very accurately. The result is named Autofocus set in APT, and it is available since 2021. So,
Ivo, can I interrupt you for a second? I think this is a critical point. So could you explain the differences between the classical V curve and what you're proposing here, your autofocus aid?
The difference between U curve and V curve, right?
Yeah, the U curve and the V curve, and why you're proposing that the U curve is more accurate?
The U curve is using all the points in order to calculate one curve, while the V curve are separating the sets and calculating two different curves. So when we have all the samples in one curve, it is self-correcting itself. We can have from the one side of the in one part of the hyperbola point that is kind of influenced by the turbulence, but the other one is closer because it just happened that the atmosphere was in different state. So the second point near the opposite side of the curve is correcting the whole calculation itself. So, yeah.
No, please go on.
Yeah. So that is the main advantage of U curve, and I cannot say that I never made comparison between the two myself because APT doesn't have implementation of the V curve, but other software has, and after we have implemented it, U curve started to appear in other applications. So this is a sign that U curve is giving advantage over V curve. Also, when we work with the whole set, it is possible to use less samples, and this leads to faster focusing. There is no need to make 20 exposures in order to have 10 for the one line and 10 for the other. Here you can use 10 for the whole for the whole calculation, and it is more than enough. This is something I want to mention, that a combination of 10 to 20 test points and minimum of 8 points have proven to work very well with various telescopes and sizes. In our implementation, there is a special calculation which evaluates each point, and if the point is not meeting criteria as good quality, it will be rejected. So we can define how many of the what is the minimum points you have to use in order to make a fit. So if we have a 10 or 12 test points, we can throw up to 4 and still get a good hyperbola, which defines a very good focus position. Also, we have made different methods of verifying that this focus is good. One is that when we are gathering the samples, it is we are evaluating how well the hyperbola is defined, and if there is need, we are adding more points. When we are adding more points, it is not sure that the calculation is exactly the best. So in this case, it's possible to make a second pass in order to verify that the focus position is the optimal one. So there are 4 methods, and 2 of them are the most popular one and giving very good results. If one is interested, can refer the APT user guide. So in order to get very good results from automatic focusing, we should cover some special requirements. The first one is not mandatory, but is very helpful. It is to choose a good starting point. For the 2 passes focusing, it is good to start a little bit away from the expected focus position. By that way, the first pass will be executed faster. If we are very near to the expected focus position, the first pass will need time and will change direction several times till it finds the good range of good range for the second pass. For V and U curve, it is good to start as close as possible to the focus position. It is not needed to be perfect, but it is good to focus by eye as good as possible. No need to use Bakhtinov mask. The very simple and straightforward focusing is enough. The more critical thing is what focusing step will be used for the taking samples and evaluating the star images. For the tools, the 2 passes algorithm, the core step should be bigger than the critical focus zone in order to get good changes in the half-flux diameter and the other metrics. And the fine step should be smaller than critical focus zone in order to be sure that we will get at least several samples in the critical focus zone, and to get one of these as a result of the autofocusing. For the V curve, any step close to the critical focus zone in steps is good enough. U curve works good between 1 critical focus zone and 2 times the critical zone. And one last thing that it is very important about automatic focusing is to compensate the backlash. But before we talk about backlash, if we cannot measure exactly what is the um, critical zone in focuser steps, there are signs we can use and to guess what is the optimal focusing step. For U-curve, when the focuser step is too small, the samples we will get will be like on the left image, and we'll see that the points are jumping in different directions, and there is no distinct or something that is close to U-shape. This is a sign that we are making too small steps, and the turbulence of the atmosphere is influencing the measurements a lot. If it is too small, it is possible not to see that we are moving the focuser at all, to detect that we are moving the focuser. So if you see jumping dots, try to extend the focusing step. When we are using too big step, this is the other corner case. When the building of the hyperbola is made, the algorithm is making one move. So in order to start gathering samples from the one side of the U curve, and when this step is too big, we will get a very defocused star, and it's possible to detect part of the donut as a star and to start evaluating it. So the shape of the dots will be something like it is increasing rather than getting lower, and after that there is a drop, and when we pass again from the away from the focus, we are getting a point when the curve will start to lower again. These kind of wings are places where the algorithm detected part of the donut, and are during the defocusing, it is getting weaker, and the half-wax diameter is starting to lower. So when you see a figure with wings, it is a sign that you have to try a smaller focusing step. When you measure the number of the microns per focusing step, APT can suggest good starting point, usually the right focusing step for your telescope. But if you cannot measure, especially if you are using Schmidt-Cassegrain or similar telescope without grade 4 focuser, with some experiments for half an hour, you will find good focusing step for your system. So when we find we calculate the good focusing position, there is need to make one move and to place the focuser in that position. However, the focusers and the motors are not perfect, and they have a backlash. And if we don't take care about that, we will not go to the exact place where the good focusing position is. The autofocus site has a special feature that can measure and calculate the backlash. It is executing 2 times the detecting of a good focusing position, and calculate what is the difference between the two the two positions. If there is no backlash or it is compensated, it will get very close values. But when it is not compensated, it is something very close to the real backlash value. Other way to measure the backlash is using half-Fox diameter, full width, half maximum inverse power Bakhtinov mask manually to see and to measure the backlash. The idea is that we have to move the focuser in out direction, and when we see that half-Fox diameter is changing, for example, record that position. After that, start to move inwards direction with very small steps. And when we see distinct change in the half-Fox diameter, to record that position, and the difference between those two positions is the backlash. The good news is again that there is a shortcut, and it is named a final inward move or overshoot move. The idea is here is that when we are want to make a outwards move to position X, we will make outward move to position X with plus 300, and after that we will make inward move in direction with 300 steps. So as a result, we will be back in X, and it will compensate the backlash without need to measure it exactly. The catch here is that this number of steps should be at least twice as the backlash. So usually it is a big number, 300, 500. Usually the 500 is working very good with f5, f6 telescopes for Schmidt-Cassegrains and slower telescopes like that. Maybe sometimes it could be 200. But definitely it is working and giving good results. So as a summary about autofocusing, we should first find the right focusing step in order to have good measurements and good calculations where the focus is. It is good to measure the backlash, but it is not critical. And if we use the final inward move as option, and also it helps to start with good focus achieved by eye. So if the A of focusing is the visual attempts to find good focus with the first telescopes, the Z is keeping the good focus automatically through the whole imaging session. As we discussed, the focus is not constant and is changing during the night. So when we have automated focuser and a good way to achieve focus automatically, we can use that to keep the focus during the night, issuing refocusing, automatic focusing, refocusing on various triggers, like change of temperature, to refocus on fixed time. Many users prefer to refocus on every half hour, no matter what, or number of taken images, definitely on changing filter. And after meridian flip, it is very good, especially not very good. It is mandatory if your telescope is suffering from mirror flop. There is need to refocus. Also, if you are very motivated and patient, you can measure how many steps are your setup changing the focuser as, how many steps per degree are changing the focusing position, and it is possible to use that number to make automatic corrections even without refocusing. Many times I have asked why APT doesn't have trigger to refocus based on the change of the star size. The answer is that this is not a good way to trigger refocusing, because the star size could change because of different events like changing the sync, jittering, obstacles in front of the telescope like trees. These are not events that are lowering the quality of the focus. Just it could be temporary.
Sky clock event closing.
So the other options are better and more productive. So this is the last slide of the presentation. Hope that it was helpful and informative. And if there are questions, I'll be happy to address them.
Yeah, there are a couple of questions. Does the APT implement both U and V curve methods, or just the U curve?
No, APT cannot do V curve. In fact, when we were discussing in the community how to implement V curve by best way, the idea about U curve has been born, and we never implemented the V curve.
And Steve asks, what is the implementation of a not flat field? If you're looking at the entire field, obviously the stars in the corners, if it's not flat, might not be round. Do you limit how far you look at the field, or you look at all stars in the field?
When you are using inverse power, there is absolutely no matter that there is a field curvature. When you are using half flux diameter, it analyzes all the images and averages them. So even if they are not perfect in the corners, there still has a size that changes when you are closing to the focus point. So even they are deformed, they will be with better quality when you are in the critical focus zone, and in the combined index, they will introduce change that you can measure.
So does your U curve have an option
part of the image intentionally? You can define that you want to use part of the image, but it is not mandatory.
You know, I don't want to say what everyone that listens to this or might watch it does, but I suspect that most all of us, including me, use a V curve in order to focus our stars. Are you recommending now that the U curve is a better solution than the V curve?
Absolutely, I think that it is better solution, and the fact that most of the active projects related to autofocusing are implementing such is a sign that there is an advantage.
And does your U curve use either full width, half max, HFD, or I'm sorry, what was the third? The inverse power? Or
yeah.
does it use all those three, or you do select it, or is it all by inverse
You can
power?
select it. In APT, you can select what metrics you want to use to measure the stars. I suggest to use half flux diameter or inverse power. Half flux diameter, not half flux diameter, full width half maximum still produce good results, but half flux diameter and inverse power gives better results.
Patrick, do we miss any questions? I think we had some commentary from our
Right, we
group
definitely
here.
had some discussion. I guess I did have just a couple of questions for you, Ivo, and on this slide that you have up, you've got the different triggers that
Yeah.
you might use to for refocusing. Does APT implement all of those that you listed here, other than the last one that you mentioned, the star size is not
Yeah, in
good?
APT, we have all these triggers available. But
And
I suppose that every application that states that has automation, session automation has something similar.
sure, sure. And then as far as your U-curve method, you had recommended that you want to start as close to a good focus as possible to start the run. So I guess the question is, how close is close enough? Like within one step size, is that or two, or is there a rule of thumb for that?
In fact, for U-curve, you can go with 2 to 3 critical focus zone as starting point, and it will give good result. In this case, if it's too far from the focus point, the U-curve method is possible to need additional points in order to calculate good U-curve. And in this case, depending on the options, it is possible to make another round just to confirm that everything is okay. And the second round, we start with the starting point found as a good point in the first pass. So it will be just make another round to make sure that everything is fine.
And what do you think about filter offsets? And how do you think that affects your focus point? I know there are offsets for most of the filters, even if they say they're parfocal.
Focus offsets are a very good solution. Also, we have option in autofocus site to measure automatically that and to record the different focus offsets. I think that combination of focus offset, especially when there are big differences in the position, and combine it with refocusing is the best way to get very sharp images. The focus offset will move you very close to the good focus position if it is not the best. And if you execute refocusing, especially with something like 10 points, it will pass for a minute or two. You will get confirmation that you are on the good point.
So basically, if you change filters, you use your offset to reposition your guess on focal zone and then run your focus U-curve.
Yeah, this is, by my opinion, this is the best scenario to keep the focus optimal. It is possible to use only the offset, but there is always kind of uncertainty because when you measure the offsets, it still can be a little bit different. If the atmosphere is not very good when you have you have determined the offset, it is possible one offset to be on the border of the critical zone, and when you are imaging with good atmosphere, it is possible the offset to become out of the critical focus zone, and you end with unfocused image for this filter. Also, when you are measuring the filter of offsets, a good hint is that the base filter should be H alpha or red filter. This should be the base because these filters gives most accurate, most sharp star images, and it is good to use that for base for detecting filter offsets.
So you're saying red would be better than, say, the luminance filter? Just
absolutely, absolutely.
Interesting.
Absolutely, yes.
The luminance are combining all the light, and especially if you are using a refractor which is not with good quality, you can get a little bit aberrations which are influencing the star image. But narrow band and red, especially from the broadband, are giving the sharpest possible stars. So they're better to use as reference when you're measuring the offsets.
And offsets are built into APT. It allows you to measure your offsets and then use that as starting points for your
Yeah,
starting.
exactly. Yeah, it will save the measured offsets in the settings, and we'll use them after that.
Ivo, you can stop presenting now with your.
Okay. Just a second.
All right. Well, let's see. I was looking over the questions that came in. I think we've got everything. So, did you see anything else there, Eric, that we missed?
There was some discussion, and I think Tim has helped answer some of the questions. Tim, or I don't know if it's Tim or Alex, so answered
About the off-axis guider and yeah, I think that seems like it's been addressed really well. So, well, Ivo, this has been really interesting. There was quite a bit of good information in this presentation, and I was interested to hear about the inverse power method that you all have come up with. I wasn't familiar with that, so I'm interested to check that out. That sounds promising. So
yeah, and the single point V curve and using the slope of the V curve that you've established. I don't want to say we all use it, but I think most everyone uses it. So if there's a better method, we're all interested in better focus.
Definitely, it is. If you are using a software that has V-curve, you can give a try with APT. APT has a time-limited demo version with all features related to hardware control available. So anyone is possible to give a try without need to be purchase something.
And if somebody wants APT, it's probably obvious. Do you want to put up a link or something where they could download the software?
Yeah, the software. Our site is www.astrophotography.app.
And I can put that into the description of the episode when we're finished with the stream. So that'll make it easier for folks to find it. All right. Well, so Ivo, I really just want to thank you so much for your presentation tonight. And you're in Bulgaria, of course. And so it was 4:30 in the morning when we started the presentation, the show tonight for you. I guess it's coming up on 6 o'clock in the morning. I think I see the sunrise starting to peek out there. So we really appreciate your willingness to get up so early or stay up so late or whatever it was for you, but to be with us here tonight.
Thank you very much for the opportunity to make this presentation. If there are questions, I'm available on email on the support email that is the site. We have APT forum where inverse power and U-curve have been born. So everyone is welcome to join. Also, we have a Discord server. So if there are more questions, I'll be happy to answer.
And when we end the stream, we shut it down. You're welcome to stay and chat with us, or you're welcome to go to bed and catch up on a little sleep, which is probably on your mind.
I will stay for a little bit while, but at one point,
okay.
I have to go to bed.
All right. Yeah, we'll stick around for a few minutes at least. So it looks like we've got everything. So again, thank you so much. And with that, looks like we're ready to check out. So Tim, if you can run the end pro, and we'll all see you later next week.
See you next week.
Bye, everyone.
Thank you.
Good night.